Hi, welcome back. In this video, we're going to talk about rectangles. If you have not seen the previous video, 6.2/6.3 parallelograms, I strongly recommend that you watch that because a rectangle is a type of parallelogram. So if we go into the definition of a rectangle, you'll see that it follows the rules of a parallelogram. We just add a few other things that make it special. Right? In our previous video, we spoke about how a parallelogram would look something like this. Opposite sides are parallel. So these lines are parallel and congruent. The top and the bottom are parallel and congruent. When we straighten out the corners or the angles and force them to be 90 degrees, which is what makes a rectangle special, notice how here we have 4 right angles, J, K, L, and M. By making it 4 right angles, it starts to affect another property. The diagonals within the rectangles will be congruent. So this distance from M to K will be equal to the distance from J to L. So a rectangle is a parallelogram that has 4 right angles and the diagonals are congruent. Okay? So today we're going to talk about how to find missing angles, missing sides, missing values giving these 2 new properties of a parallelogram. So here's an example. We know that this quadrilateral is a rectangle, so I want to find the missing measures. First, we can begin by finding very straightforward lengths, right? PS is going to be congruent to QR because it's still a parallelogram, so opposite sides are congruent. Now that's 10. That means that PQ will be congruent to SR, which makes this 24. So I can fill in QR to be 10 units, SR to be 24 units. Now, because this forms a right angle at every corner, we can also focus on the length of the diagonals. So if I wanted to find the length of this first diagonal as Q, I can see how this is a right triangle. I can focus on this triangle right here. And we've spoken before about right triangles in the Pythagorean theorem. So I'm able to find this length, the diagonal length, by saying a squared plus b squared equals c squared. I can use the Pythagorean theorem to solve for the missing piece. And the diagonal is what's missing. So we have 10 squared plus 24 squared equals c squared. 10 squared is 100. 24 squared is 576. When I combine them, I get 676. And the square root of both sides gives me the diagonal, which is also known as SQ. The diagonal will be 26 units. This right here. Now, because the rectangle has a particular property where the diagonals are the same, I can say that PQ will be congruent to PR. So PR should also be 26. And then QT, if I find this distance, from our previous rules of parallelograms, this is still true. The diagonals bisect each other. So this is still going to cut the segment into 2 congruent segments. So if I know the whole distance is 26, I can say that half of that will be 13, making this 13 and 13, where the total is 26. In these following 2 examples, we're trying to find different values. So let's start with the first one. Whenever you're given a problem, you're going to want to write down the problem. So feel free to pause. Feel free to write this down so that you can label the picture. RT, this length, measures 5x plus minus 14. US, the other length, I'll color this something different in red. US will measure 2x plus 10. I'm trying to find the length of VT. First, I need to find a way to relate these two lengths. The diagonals are congruent for rectangles. So here's my setup. 2x plus 10 should equal 5x minus 14. Once I find the relationship and solve for x, I can plug it back in and find what I'm really looking for, which is VT. I move 2x to the other side. 10 equals 3x minus 14. I move the 14 over. 24 equals 3x. When I divide both sides by 3, I get x equals 8. Now, what I'm interested in is finding the value of VT. VT is just this portion. Now, since this is the midpoint of both segments, it cuts it into two congruent segments, I can then just take the length of RT, the whole thing, and cut it in half. And since RT represents 5x minus 14, I can plug x into this equation. 5 times 8 minus 14. 5 times 8 is 40. When I subtract 14, I get 26. That is the full length of RT. I want half of that length. Therefore, VT will just be 26 divided by 2, or 13. This is why it's important to have been able to know and understand the properties of a parallelogram. So if you did not watch or understand what 6.2/6.3 is about, those rules will apply into this rectangle. Let's try this next one. VW is 9x minus 11, so I'm going to label VW 9x minus 11. SU, the full length, is going to measure 16x minus 12. How are these two related? First, we need to understand that these two lengths are not equal. This length is only half, while the other length is the total. So when we set up an equation to relate them, we need to know that 9x, the entire length, from V all the way to T, will equal 16x minus 12. Therefore, I need to take the 9x minus 11, and I need to double that length, multiply it by 2. And that will equal the full length of the other side, the other diagonal. And now I distribute, solve for x, I do my thing. So I distribute, I have 18x minus 22 should equal 16x minus 12. As I isolate the variable, 2x minus 22 will equal negative 12. When I move the 22 over, I get 2x equals 10. Therefore, I'm leaving with x equals 5. Now, this question is asking for the length of WT. WT is this portion from here to here. So, that portion is half of the full length of blue line, VT. So I know that this length will be congruent to this length. And since I was already given VW up here, I can plug in the 5 into this portion because it just represents half of the diagonal line VT. So WT is equal to VW. So I plug it into VW. WT equals 9x minus 11, which is 9 times 5 minus 11. Therefore, 9 times 5 is 45. When you subtract 11, the length, half the length of the diagonal, results in 34. The key thing is understanding what am I going to plug this back into? What am I looking for, and what relationship do I want to plug it into to find out the length, the desired length? In these next two scenarios, we have more rectangles, of course, and I'm given different information. As you can see here, SU, this full length, will equal x squared plus 3x plus 5. And the other diagonal, VT, is equal to x squared plus 7x minus 39. How are these two related? Well, the diagonals are congruent, so I'm going to set them equal to each other. x squared plus 3x plus 5 will equal x squared plus 7x minus 39. It doesn't really matter what they represent as an expression. We know that the diagonals are equal. So if you have quadratics, set them equal to each other. If you have a regular algebra 1 problem, set it equal to each other. No matter what you're given, those two diagonals will always be the same. And then once I have my equation set up, I can solve for x. So I can start moving things around, and I realize that the x squares are going to cancel out. 3x plus 5 will equal 7x minus 39. As I move things over and I combine like terms, I have 5 equals 4x minus 39. If you move the 39 over, 5 plus 39 results in 44. Therefore, x results as just 11. Now, I'm interested in solving for SU, which is this full length. So I need to plug it back into that. I take my 11 and I plug it back in here for every single x value. I plug it in here and in there. So I have x squared plus 3x plus 5. When I plug it in, I have 11 squared, 3 times 11 plus 5. 11 squared is just 121. 3 times 11 is 33 plus 5. As I start to add things together, 121 plus 33 plus 5, I get 159. SU, the full length, will equal 159. If you look at this next example, I'm given another set of diagonals. RT, this length, will equal the square root of 8y minus 4. The other diagonal, SU, will equal the square root of 7y plus 3. Do not let the fact that they're square roots or quadratics change the fact that these two lines are really just equal to each other. Diagonals are congruent for rectangles. And that's what I'm going to do. The square root of 8y minus 4 will equal the other one, 7y plus 3. Once I have my equation, I can solve for the variable. Now, to get rid of the square root, we do the inverse relationship, right? The opposite of square rooting is squaring. So I'm going to square both sides. The square root and the square are going to cancel each other out, leaving me just with 8y minus 4 equals 7y plus 3. And now I can just solve for y. Move the 7y over. Y minus 4 equals 3. Move the 4 over. Y equals 7. And for this one, we don't have to plug it back in because we're just looking for the value of y. So the two biggest things that we've spoken about so far is the diagonals are congruent and the corners are 90 degrees, which opens up problems to Pythagorean theorem and anything right triangle related. For these last two examples, we're going to be using graphs. So feel free to grab graph paper, feel free to pause the video, draw these pictures yourself, because watching the video alone doesn't do it all the time, right? Make sure you draw this out and you solve it with me. So I'm trying to identify that this quadrilateral, I want to determine whether or not it is a rectangle. So I'm going to draw the points. A is located at negative 3, 1. This is A. Negative 3, 1 is A. B is negative 3, 3. Negative 3, 1, 2, 3. C is 3, 3. And D is 3, 1. Now, if I connect these points, I know that this already looks like a rectangle, right? But how do we prove that it's a rectangle? Well, for one, we can show that opposite sides are congruent, right? We can also show that they form right angles, which we'll get to in this next example. But for now, if I wanted to use the distance formula to prove it, I can use the distance formula to show that the opposite lengths are the same. x2 minus x1 squared plus y2 minus y1 squared. Now, if I check that the opposite sides are the same using the distance formula, I'm really just proving that it's a parallelogram. To prove that it's a rectangle, I need to find the distance between the opposite points using the distance formula. And then I need to find the distance of the other side. I'll do it in yellow or in orange. Those two distances should be congruent. That will prove that it's not just a parallelogram where the opposite sides are the same, but that the diagonals are the same. So I would use those opposite points, right? I would want to use this point and this point to find the distance. So I have -3, 1, and 3, 3. When I plug this in here, I want to know whether or not this distance matches, let's do this in orange, the other ones, the distance of the other diagonals. So the other points I'm going to want to use are -3, 3, and 3, 1. All I would have to do is identify my x1, y1, x2, y2, x1, y1, x2, y2, plug it into the formula, and find the distance. And then I would do this again, x1, y1, x2, y2, plug it into the formula, and find the distance. And then the question is, are these distances equal? If the first distance matches the second diagonal, we have ourselves a rectangle. Now, because we can see in the picture, and this picture is sort of like a horizontal one, you can just see the diagonally they're going to be the same, right? We can count the squares. We can see that those distances are the same. This method is mostly used or useful when the rectangle is more of a tilted way, right? When it's done sideways. If the triangle was drawn something like this, then I would be able to find the diagonal distances, right? I would want to know, is this distance equal to this distance? So let's check out the next example. Here, I want to determine whether it's a rectangle, but I want to use the slope formula to identify whether or not it is a rectangle. Let's first start by plotting, and then I'll explain what this means. Let's start by plotting the points. The first one is at -3, 0, -2, 3, 4, 5, and then it keeps erasing on me. 4, 5, and 3, 2. When I connect these, this already looks like a parallelogram, but is it a rectangle? Now, to use slope formula, the way that we're going to do it is we're going to first identify the points that we're working with. This point is A, this point is B, this point is C, and this point is D. A rectangle forms 4 right angles. And the way we use slope is that when the slopes are the same, it forms parallel lines. But when the slopes are perpendicular, right? Like let's say that I'm focusing on 2 lines, AB and BC. If I want to show that those form a right angle, I can say AB is perpendicular to BC when the slopes are negative reciprocals of each other. So I would find the slope of 1, and I want to make sure that it's flipped, and I change the sign. If the slopes are negative reciprocals of each other, then by default, the lines are perpendicular, which means they form a right angle. So I can find the slope of AB. If I want to find the slope, or M, I would do rise over run. So the slope here is up 3 over 1. And then I can look at the slope, right? I count it 1, 2, 3 over 1. I can look at the other slope, up 1, 2. So from BC, the slope would be up 2 over 1, 2, 3, 4, 5, 6, up 2 over 3. 2/6, which simplifies down to 1/3. As you compare these slopes, notice how 3/1 is not a negative reciprocal of 1/3. The slopes was flipped, but we did not create a negative reciprocal from it. And that was a key component. The slopes are flipped, but it's not a negative reciprocal, which then creates not a right angle. They're not perpendicular to each other. And since one angle is not perpendicular, I don't have to check all four corners. I just have to check if one of them was 90 degrees. Since it doesn't pass the test, there's no need to check all four of them. If it had passed the test, I would have gone through all four corners and checked that the slopes were negative reciprocals. That's the key component. If the slopes were parallel, we then would have said that the slopes were equal to each other. But we were looking for negative reciprocals. All right, guys, I hope this has helped. Please let us know if you have any questions. Don't forget to like and subscribe if you haven't already. And as always, we'll calculate later.